All right, folks, let's start. Okay. First of all, can you guys hear me? All right, thank you, Josh. All right, let's start. This is ECE 318, and this is our 6th lecture today. And first of all, according to the Gantt chart, we are at this particular cell, which is the last lecture for Module 1, Semiconductor Material and Diodes. So after today, we're gonna have a new module, which is 2 Diode circuits, and after that we have midterm 1. Okay, so if you recall, in the module 1 here, we're gonna have a exam time survey. Yeah, remember to do it. I noticed that most of you guys have already done it. I really appreciate it, and if you haven't yet, please be careful. The due date is 24th. Okay, 24th. All right. That's a little bit non-knowledge related information. And other than that, let's talk about the diode. And last lecture, we talked about the diode DC analysis. Okay? DC analysis in DC circuits. So today is for AC analysis for the diode circuit. But before that, let's once again summarize the DC and AC analysis. Let's become once again familiar with the concept, or say the idea about it. Okay. The DC AC analysis means what? Now they mean this. So given the circuit, you might have DC source and AC source, and they respectively introduce the DC analysis and AC analysis. Sounds very natural, right? Very natural. And instead of DC analysis, you have a DC model of diode. Of course, in later modules, we will see the DC modules of the transistors. However, this idea remains same. Okay, this overall idea remains same. And also in AC analysis, you have AC model, okay, which is actually called small signal model. Because we, generally speaking, don't call AC model. We call small signal model, right, of the diode or transistor in future. Okay, remember this name, small signal model. And when we talk about a small signal model, we need to bring up the concept of small signal and big signal. This is something we have learned before. What does it mean by big signal? A big signal is, generally speaking, nothing but a DC. Big signal. AC, small signal. This is due to the big DC voltage and big power versus the small voltage and small power for AC. Okay, so call them big and small for reasons. Because the DC analysis, the DC voltage is really big. The power is relatively bigger as well. Okay. In AC analysis, the AC source voltage is very small, much smaller. Okay. And the power correspondingly much smaller as well. Okay, so big or small, they do have reason. Okay, they do have reason. So this concept needs to be very clear. Now, why we are conducting DC analysis and AC analysis? Very simple, because we have both sources. In other words, if in a circuit you only see DC source without any AC source, of course DC analysis only. Doesn't make sense. And vice versa. Only have AC source, then no bother for DC analysis. It doesn't make any sense. Right? However, both DC analysis and AC analysis, I should continue from here. Okay. However, there's no space, so continue from here. So both DC analysis and AC analysis going to introduce like results respectively, right? The total result. By result, it might means one voltage or a current. Okay. It might be a voltage or a current, not power. Okay, not power. Maybe you see why it's not about power. Okay. This total result, once again, either voltage or current equals what? DC result plus AC result. And this is what? This is what principle? Anyone knows? Why? The total result equals DC result plus AC result. What is that?
Superposition.
Excellent. Very good. Josh is right. Superposition. Very good. This is the basic principle we follow to come up with this. Okay. So if you're looking for a given circuit, if you're looking for a voltage, one voltage or current in this circuit, and then you see one DC source and one AC source, or even multiple DC source and multiple AC source, what do you want to do? Respectively conduct the DC analysis and the AC analysis, and the total result, you just sum them up. Superposition, the superposition. And generally speaking, in our diode and transistor circuit, we're going to see one DC supply and one AC input source. So you only have one here and one here. Therefore, one DC analysis and then one AC analysis, respectively. Okay, they are independent. Can you tell that? They are independent. Okay, respectively conduct DC and AC analysis, and then sum the result together equals the total result. The total result. Okay, this is superposition. Okay, and this is also answering why we are conducting DC and AC analysis. This is why we keep talking about DC analysis and AC analysis through the entire class. So, and why? Because in diode circuit and especially transistor circuits, we always gonna have DC supply and one AC input source. So we have both. So we have to respectively conduct DC and AC analysis. Okay, this is the bottom line concept. You need to understand like a 1 + 1 = 2, and then you can further derive any advanced math, right? So this is the 1 + 1, why we are doing this, all right? So we have done quite a bit, several examples for DC analysis of the diode circuit, and today we're going to talk about AC as the last lecture for this module, right? If this idea is clear, and then we come back to the PPT slides here. All right, AC analysis, AC analysis. Let's see. Here is pretty much repeating what I have just presented on the paper. So the total voltage, a total current, not necessarily to be the voltage across the diode, or not necessarily to be the current through the diode either, right? No matter which voltage, which current inside of the circuit, they're always equals to the DC result plus AC result. Can you see the case-sensitive letters? Okay, they're respectively representing the DC result and AC result, right? Obviously, this column is DC, this column representing the AC, right? So they're case sensitive to represent DC and AC respectively. Okay? And DC results might be whatever the result out of the DC analysis, and AC result is whatever the results out of the AC analysis, right? So the total signal, either voltage or current here, the total signal looks like what? It looks like this blue curve. From the blue curve, first of all, the DC value of this blue curve is equals to what? Anyone remember? Given the signal, what is the DC value of this given signal? How can we tell? Anyone remember the first lecture? Even the signal. How can we tell what is the DC contained? Anyone remember?
Take the average.
Excellent. Connor is right. Take the average. Okay, to find the average value. So look at the blue curve here. Okay, sinusoidal. Look. However, what's the average of it? It's the middle line, right? The middle line, be careful, is not zero. Okay, the middle line is not zero. This middle dash line is not zero, because the zero is here, right? The x-axis is on here. So it has a DC offset, right? DC offset, which is nothing but DC value. You take the average value of the blue curve and you end up with this DC value here. And that's actually, we are talking about the current. This is how we got the DC here. And this, or say let's say how we interpret this blue curve. Okay, this the average value is the horizontal dashed line, which is indicating the average value. And that's the DC. And then what's the AC? AC is a sinusoidal in blue color, right? In blue color, so it's sinusoidal. So this sinusoidal is just equals to the magnitude, which is the magnitude here, from here to here. Here is equals to capital IFD, and then the sine omega t with certain frequency, of course. Okay, so this blue curve, from here you can tell the average is at I sub dq, which is not zero, so it contains DC output result. Meantime, there's a sinusoidal here, which is the result out of the AC. It's not surprising that we are seeing both DC and AC source, of course. And we have both sources. That's why the result is going to be the superposition between two as well, right? So this is, again, bottom line idea about DC and AC analysis. All right. Here, also here. There's a concept actually in the textbook as well. It's called Q point. What does it mean by Q point? Q point is nothing but the DC result. Okay, keep this in mind. What does the Q point of the diode means? Q point of the diode or future transistor means the DC result of the voltage across it and the current, of course, DC current result through it. All right, so Q point means nothing but the DC result. All right, keep this in mind. The textbook use this term a lot. Okay. Right. And then superposition obviously further means how to conduct the DC and AC analysis. How to, we'll just split the given original circuit here to DC circuit and AC circuit respectively. Right? How to come up with a DC circuit from the original circuit? Well, you eliminate the AC source first, right? How to eliminate it? It's up to what kind of DC AC source this is. From the simple here is an AC voltage source. So how to eliminate a voltage source? We learned this from the from circuit 1, right? If a current source, how to eliminate it? Open. If a voltage source, how we eliminate? Short, right? Be careful, independent source, okay? Both here and here are independent, so we can eliminate them. If dependent source, we cannot touch. Remember, we cannot touch, okay? Has to be independent. And if they are, then just a short voltage source and open the current source. All right. So here is voltage, so we short it. That's why in the DC circuit, we're not seeing the AC source anymore. It is shorted out. It's shorted. It's shorted. Okay. And the diode is replaced by what? DC model. Right. A power supply, a DC voltage supply with voltage of the cut-in voltage V gamma, right? So diode is replaced by DC model. That's very natural. Keep the resistor, and the output we're looking for is a DC output result rather than the total one we are looking for. On the other hand, in the AC analysis, what do we do? We need to find AC circuit. AC circuit, what we do? Keep the AC source, eliminate the DC source, right? Eliminate the DC source, what do we do? Short it as well. Short it, because the DC source is a voltage source. Replace the diode by what? Small signal model. Remember, we just mentioned small signal model, right? So here, of course, this is something new. This is something new. What is the diode small signal model? Very easy, very, very easy. Okay, this is the formula you want to keep on your cheat sheet, or say formula sheet. Diode DC model is a voltage supply with a voltage value of V gamma, and the AC model, AC small signal model, is what? Is a resistor with resistance value of VT over ID. Let's take a look at this formula. Okay, who is the denominator ID? Who is it? Anyone knows?
DC,
Small signal model. What is it, Kevin?
DC current.
Excellent. Very good. Take notes if you need. Okay. AC small signal model RD is equals to, or say in terms of DC current result. That's a very, very important thing. It's a DC diode current. DC diode. Very good. Okay, very good. Very good answer. Okay, this is the denominator, IDQ. Who is numerator? VT is what? Who knows what this guy is? Anyone can remember? VT is what? Anyone remember this? This is something we learned from previous slide. It's probably a little bit hard to remember, but VT is called thermal voltage. Thermal voltage. Yeah, and it equals to, generally speaking, 26 what? Millivolts. Okay, be very careful. It's not volts, but millivolt. It's constant. Very nice, constant. Temperature dependent, constant. However, we generally speaking assume it to be 26 millivolt. So in AC circuit, diode is replaced by the small signal model, RD. So from this formula, RD formula, we can also tell one thing: the order of the problem solving, right? Well, the given circuit is split to DC circuit and AC circuit to conduct DC analysis and the AC analysis respectively. However, which one should go first, or it doesn't matter? What do you think? Anyone?
I'd probably do DC first.
Why is that?
You need some of the values for the AC analysis.
Exactly. Okay. Very good. Very good. Okay. So remember, you have to do DC first, because without DC, you cannot have IDQ here. Without IDQ, you cannot have the small signal model, let alone AC analysis. All right. So DC analysis goes first. In the transistor circuit, the same. Okay, same idea. Right? In transistor, AC small signal model is in terms of DC result. So DC analysis always goes first. All right, very good. Okay, I gave you this first. Okay, this goes first. This one follows. Here, once again, is emphasizing DC analysis model is a voltage supply, V gamma. Small signal model is RD, resistor. Right? And this is trying to summarizing how you come up with the DC circuit and AC circuit, small signal circuit. To DC circuit, we know we need to eliminate the AC source. No problem. We have mentioned this. How we do it? Short the voltage source and open the current source. Of course, independent source. Also, we might need to also take care of the what? Capacitors, right? In DC circuit, what we do to the capacitor? Open it. This makes perfect sense if you recall the 235. In DC circuit, do we have any capacitor? No. Capacitor is considered as open circuit. Then how about the inductor? Opposite, right? Which is short circuit. Does that make sense? So in DC circuit, open capacitor, short inductor. And eliminates the AC source. Right? And of course, the diode is replaced by DC model. Well, a DC supply or DC battery with V gamma as a voltage value, that doesn't matter. Okay. What name you call it, that doesn't matter. Right? This is how you come up with DC circuit. Because obviously, without circuit, you can't do any analysis. That doesn't make any sense. So the first thing you need to get the circuit, right? And then AC circuit. How to find the small signal circuit? We know we need to eliminate the DC independent sources, following the same idea. We also might need to take care of the capacitors in AC. Small signal circuits, remember, capacitor is considered as what? Short circuit. Okay, short circuit. Short circuit. Okay. So remember this. Capacitor is considered as short circuit. Okay, remember this. And also, of course, the diode is replaced by the small signal model, which is the small resistors, or small resistor. So here, a little bit more about the capacitor, under the dot count. In DC analysis, we just mentioned C is open circuit, AC small signal analysis. Capacitor is short circuit. And let's explain a little bit why. Okay, this is because of the impedance of capacitor. We mentioned a little bit in the lab and the previous lecture. Impedance of the capacitor equals what? Negative J over omega C, right? Well, the omega equals to 2 pi f. So first of all, in DC, omega equals to what? In DC. Anyone knows? In DC, what's the omega? Omega equals to 2 pi f. Then let's ask instead, what's the frequency of the DC? Anyone knows? Very good. Kevin is right. DC frequency is 0. It's 0, no problem. You can consider DC as a special AC with 0 frequency. And that's not wrong. Okay? That's not wrong. There's no frequency. Period equals to infinity. Of course, constant horizontal line is forever. Of course, it's a infinity of period. Therefore, 0 frequency. Well, according to this, then, what is the impedance of the capacitor in DC then? Because of this, what is it? Infinity. Infinity impedance means what? Does it make sense now? Right. Same thing in the small signal analysis. we are thinking of the frequency again. Frequency is what? It's high. Okay? It's obviously not infinity. However, it's high, right? Frequency is high. Then what is the impedance? Low, right? So if your frequency is high enough, then we just consider ZC as 0. 0 impedance means what? Short circuit. All right, this is what, okay, this is why we have open circuit and short circuit respectively for capacitor in DC and AC, okay? So this has reason. It has reason. It does have reason. So now let's do a little bit exercise here. So according to the summary here for DC and AC circuit, given the circuit down here, I give you guys kind of 3 to 5 minutes to come up with the DC circuit and AC circuit respectively. Because obviously in this circuit you have, well, this is what? AC source. This is what? DC source. You have both. Of course, you can split it, right? Into DC circuit and AC circuit, respectively. Okay? Without any circuit analysis yet, just to come up with the circuits. Okay? Just go ahead, try this for 3 or 4 minutes. Okay? Go ahead. Repeating this DC circuit once again. So this DC circuit, you need to open 2 capacitors C1 and C2. Therefore, two portions of the circuit are gone. So only 1 diode, 1 RC, and 1 VC left. And then you short these 2 grounds together, end up with this DC circuit down here. Replace the diode by the 0.7 volts supply. You can have the DC circuit, complete DC circuit, from where you have to find the current of the diode as one of the unknowns. Okay, and no matter what problem is asking for, current through the diode must be found for later on AC analysis. Okay. Any questions for DC? If this makes sense, then we can move on. What is the AC analysis? What is the AC mean? Is that updating the page, number 6 now? Is it? That's fine. It's recorded.
And yes,
You can see
my side now.
this is number 6, right?
Yeah.
Okay, good. We continue. And here we keep the C1 and C2 this time by shorting them and short out the DC supply up here, right? And then this is the result of AC circuit. And of course, diode becomes the AC small scale model, which is RD. Does it make sense? But this is the result of the AC circuit. Take a look. I'll give you guys like 10 seconds to see any questions. That doesn't make sense. AC source remains. RL remains. RC remains. But you flip it down again. Short this ground with this ground. Right? Easier to see it. This is the AC circuit. From here you can do like a nodal or even mesh, whatever you want, to find out whatever is being asked. And RD, of course, once again, equals to VT over IDQ, right? This is the DC and AC circuits. Okay, we are emphasizing the circuit here. Circuit here. Any questions regarding the circuits? All right, if they're fine, we can move on to the next. This is the one example, a very simple example. However, is trying to clarify the procedure again by a specific example. The given circuit, the original circuit is up here, including one AC source and one DC source. Of course, we're going to conduct both analysis. It's telling you the source voltage. DC is large, 5 volts. AC is small, 0.1 volts. AC, large and small. That makes sense. And the cut-in voltage is 0.6 volts, not 0.7. Be very careful. And the resistance of 5 kilo ohm here. So, first of all, the DC circuit is like this, right? AC source is shorted up. Diode is replaced by 0.6 volts. Inside of this circuit, you find a V naught here. The AC circuit here, the diode is RD. And short out the DC source. And the V naught is here. Obviously, the total V naught here we are asking for equals to the sum of capital V naught and lowercase v naught. Right? The idea is very clear. The idea is very clear. Okay. So let's try this out. Very simple example. I gave you 4 minutes. You try this out. Find the total V naught. 4 minutes. Go ahead. Well, I see Kevin already got the answer. I think it's about time to show the solution. Can't remember if his answer right or wrong, but not too bad. Not too bad. Let's see the DC analysis first. Okay, the circuit up here is obviously DC circuit, and we got no matter what. Remember, we have to find IDQ, right? Does it make sense? It's required. It's must, because without this guy, we cannot conduct the AC analysis. Okay, even though the problem asking for V naught, we still need to find out IDQ. Okay, this is a non-negotiable. So IDQ is over there, 0.88 milliampere, okay, as the basis of the AC analysis model. V naught equals to 4.4 volt. It's a very straightforward. It's actually by the current flow through this loop times the resistance. Single loop circuit. 4.4 volts as the V naught in DC. The AC circuit. Now you see, we are applying this DC IDQ. Right? And then we end up with 29.5 ohm. 29.5 ohm. With this resistor, and then V naught is actually applying a voltage divider, right? Just a voltage divider. Of course, here a little bit tricky that the 29.5 compared to 5 kilo ohm is nothing, right? So it pretty much basically occupy almost every single volt out of the AC source. It's very close to 0.1. Very close to 0.1. Right? And a sine omega t here. Right? This is the AC. Total result is sum of 2, as we have discussed. I think Kevin just had a little bit rounding issue, and other than that, he's fine. Pretty much fine. All right. So this is the solution for example 1. Take a look. See any questions you have. Any questions? Anywhere need to be discussed tomorrow? All right, if this is fine, then example 2, I leave it to you guys to do after class exercise. Pretty much same idea, exactly same circuit, so it doesn't waste our time in the class. Okay. Equals this, and from here, I actually today I'm gonna also talk about our homework 0 solution. Okay, some of the homework 0 problem I need to talk about. One of the problem, if you recall, is also what? 1 DC plus 1 AC result, which you cannot combine. Okay, you mathematically you probably can combine like one real number and one real number and one sinusoidal phasor. You probably think you can combine them mathematically. Yep, the calculator is going to do this for you. However, conceptually, you cannot. Okay, because one is DC and the other is AC. You mixing them together, okay, just to have a plus in the middle. That's all. That's all you can do. Okay. If you mixing them together, it becomes one phasor. That one phasor representing one single AC. You cannot a DC contained inside anymore. Does it make sense? So when you're expressing DC plus AC mixing together signal, and then the only thing you can do is have a plus in the middle. You can't do mathematical combination, right? So this is the example 2, and example 3 is actually very easy example, but just to get used to the statement here. First of all, telling you there's a diode. Of course, it come with some certain circuit and telling you the IDQ equals 1 milliampere, or say is biased. Okay. Q point, biased point, is biased at somewhere. All of these statements are meaning the same thing, which is DC result. Okay, keep this in mind. So it's biased at this Q point, which is 1 milliampere for current through the diode. Okay, so this is telling you what? This is the DC result, right? This is nothing but DC result. The DC result. A bio-DC source, specifically, we don't need to worry about. And then such diode, if an additional AC source, meaning DC result you already have, and you don't need to worry about anymore. Additional AC source going to introduce additional AC analysis, right? Inside of this AC analysis, AC current resulted is this. And then find what is the applied AC voltage. It's actually very easy, right? First of all, from the DC result, you can find what? AC small signal model of the diode, 26 ohm. Right? So applying a voltage, AC voltage on this guy resulted in AC current like this. And what do? Ohm's law. This current is introduced by this applied AC voltage. And then just Ohm's law, you find the applied voltage across the diode. That's it. So this problem is nothing but reminding you how you interpret the given. Okay, if a DC biased or say Q point of the diode is given, then you understand, okay, the DC result is already given. We don't need to worry about it anymore. And with this DC result, you immediately come up with the AC small signal model, RD. And from there, you conduct the AC analysis. So this idea, this workflow need to be established. Any questions? All right. Once again, DC goes first, okay? If you have both DC and AC source, DC goes first. Okay? Then second, AC small signal model circuit model, RD, means nothing but RD. Okay? Relies on the DC current of the diode. Once again, same idea applied to the transistor circuit later on. Okay. Here is something minor, but also need to be brought up. The diode is actually the model is actually the real practical model, non-ideal model is very complicated. It has internal capacitance, okay? Internal capacitance. So much more accurate model, or say the representation of the diode, is like this. As resistors and the capacitors, okay? Parallel and series connected. And they have respectively different names. AC small signal model RD is just one of them. You see it? RD is just one of them that we are using in this entire course. However, the complete model in much more involved. Okay, much more. Any questions about the AC and the DC, the diode? The circuit is fairly easy. You do need to conduct a little bit circuit analysis. You do need to conduct a little bit circuit analysis from 235. Okay. Other than that, it should be fine. This is the slides for today. And the next, I just want to talk about the homework. Well, this is the solution I have posted in Canvas. But I just want to go through them together with you guys to see any more questions or concerns. Of course, but to be honest, the homework zero it's not easy to get a very good grade. It's not very easy to get good grade. So we do have one student get 10 out of 10, which is very, very impressive. And obviously he understands the details very well. Good job, good job. And also we have 2 or 3 students get 9.5 out of 10. Very impressive as well. Okay, and so keep up. Okay. Anyways. First problem, I think up to here, everybody is fine, except some impedance here. The impedance here must including the J, okay? J is part of the impedance for capacitor and the inductor. You can't miss the J. J, as you know, is the imaginary number unit, and you can't miss it, okay? The impedance R, C, L are listed here. Frequency as 377. The rest of the thing just algebra. Okay. Here, because these is the calculation operation among bunch of complex numbers, so best way to conduct them is using your calculator. Okay. So make sure your calculator is very handy and very easy to use in not only the operations, but also the conversions between phasor and complex number, okay? Whichever way you feel comfortable with. Okay.
So Kevin asked when the grades will be uploaded.
The grades? Oh, has anyone noticed the graded homework has been returned back into the same place you submit? Has anyone noticed that? I re-upload. Okay, good. It's already there. Okay, and re-upload the graded homework back to there. Anyone else also notice this?
Mine is not uploaded back into there.
You're not seeing yours, but Daniel did. But first of all, do you know where to check it? Is that clear?
So you go into homework 0, and then you go down to the submission part, and then in the comments you reattached it, right?
Correct. So what I'm doing, you see here, what I'm doing is just here. Let's see. Yep.
Okay.
Done. We took the files you uploaded, which means me. Okay, I've uploaded the graded homework back to you guys. Okay, this is what I did. Okay. This is what I did. So which means you guys not receiving any notification for returned homework, right?
No. I think I got like something that was buried in with everything else, but not like an explicit grade or anything.
Yeah, probably not.
Like if you could just send like a general email once you've uploaded all those, I think like we know that to look for it.
I see. I thought you guys gonna receive a notification automatically, but if not, I will try to remember to send a notification. Will graded homework returned, something like that. Email 25. Return. Well, we can continue here. And so the second question here is actually the source is AC plus DC. Okay, look at the format given, the given source there. Oh, Daniel bring up a good point. Daniel say, I think it's because we don't have a specific grade tap. Well, first of all, the homework, you mean, let me see. Let me see if you have, you're talking about grades here, right? Here, you do have the tag here. You do have the homework tag here. So I'm probably gonna manually type in the homework grades here so that you can see it. I think that's a good point. I will do so then. But because the thing is, everyone's grades is actually recorded on an Excel sheet for my own record. I'm not relying on the grades in the canvas to calculate your grade. So that's why. Because a lot of handwritten works and the grades there is not automatically updated, right? So if I return the graded homework, you can know your grade as well. So that's why I'm not relying on this canvas grade. Okay. We can move on here. And based on that, obviously, when the source is DC here, capacitor open, inductor short. Short inductor here inducing a current flows through it just equals to the total source current 5 ampere. That's why you have a 5 ampere DC here in addition to the AC result. Okay, so this result is obviously a superposition between DC and AC. Okay, that's how it end up with this. And once again, you can't do any further combination between these two because this means one DC plus one AC. You combine them together, it becomes one single AC, then it doesn't make any sense. Because DC plus AC won't give you AC, remaining as DC plus AC. This is how we interpret this problem 2. Problem 3 is actually in my opinion, the most important problem, and the concept need to be very, very clear. Let me repeat the circuit here and talk about it maybe a little bit. Let me find the circuit here. Right here. So you have 10 volts here. You have one kilo here and 0.2 kilo. Most of you guys did this problem very good, but there's just a couple of students seems 235 need to be refreshed. Okay, this is the V1. Okay, we are looking for this. So we are looking for V1 equals to what? Now, realizing V1 equals to what, meaning what? From V1 this node with respect to the ground, from here to here. Because this is ground. And since this is ground too, you can feel free to short this too to see the loop. Because I'm seeing several of you guys are still trying to see the loop without applying the pass KVL. That's fine. That's not wrong. However, pass KVL It's much easier. Okay, it's making much more sense actually. And but to hear how to do this problem, Okay, you have more than one way, and you can do a KCL at this node. If you do KCL at this node, what is the current here? What is the current here? Either this way or this way. Anyways, this branch current is what? What's the current here? KCL at this node, you might assume a voltage current go upward, towards right, go downwards, 1, 2, 3, 3 current, and this is the another branch. This is the last branch, which is the fourth current. What's the current here? Zero, absolutely zero, absolutely zero. This is the open circuit. You have V1 as voltage. However, it's an open circuit. There's no current. Okay, so there's no current involved here. So KCL at V1 is equals to how to write it. Going up, current is equals to V1 minus 0 divided by 1K plus V1 minus down 0 here divided by 4K, right? Total current of these two equals the current entering it. Entering the current is equals to what? Equals the current goes through 0.2 kilo ohm. The current through 2.2 kilo ohm equals to the voltage across the 0.2 kilo ohm divided by 0.2 kilo ohm, right? Who is the voltage across 0.2 kilo ohm? Who is the voltage across 0.2 kilo ohm? It's absolutely not 10 volt. Absolutely not. 10 volts is here. Is supposed to be what? 10 minus V1. Okay. From 10, which is here, minus V1, which is here. 10 minus V1. Right? So one equation, one unknown, we got a V1. And which is I1? I1 is here, right? Is this I1? Can't remember. Is this I1? Anyone remember? Probably you don't either. But anyways, if that is I1, I1 equals to what? Oh, I1 I think is going downwards. It's defined as going downwards.
The other way. Yeah, it's facing downwards.
Going downwards. Then it equals to what? I1 going downwards. How do we introduce the I1? I1 is the current flows through I1 kilo. So the voltage across 1 kilo divided by 1 kilo equals to I1. However, since it's downward, then the voltage must be following such polarity. Positive on the top, negative on the bottom. However, the bottom is V1. The top is ground. So is 0 minus V1. This is how we come up with the I1. So this is a quite pretty much 235 circuit, 235 circuit. And of course, at the beginning, if you don't like the top ground here, what you can do is convert that circuit to equivalent circuit. Your 4K remains, your 0.2K remains. However, you flip your 1 kilo ohm resistor, flip it down, right? Like this. This is the equivalent circuit. From here, you might feel much better, isn't it? And if you're looking for V1, this is what? Voltage divider, right? The voltage divider. You can do this as well. Same thing. The voltage divider V1 equals what? Total V 10 times numerator is 1K parallel with 4K. Denominator is 0.2K plus 1K parallel with 4K. Does that make sense? Okay, so either way, you can end up with the same answer. Okay, either way, end up with the same answer. You can do this, flip the original circuit, flip original 1 kilo ohm down. So this is the problem 3. As to problem 4, it's actually just a little bit algebra, just algebra. It's might feel like a little bit tricky, but nothing more than algebra. Yeah, nothing more than algebra. So from the input end, you're doing a voltage divider. From the output end, you're doing second voltage divider. Just to be careful, the the number. Okay, 2 mega over 3 mega. This is what? This is a 4 over 5 times 10 to the 4. Okay, be careful. 10 to the 4 and times V. And from here, you can divide V naught over Vs as the voltage gain. Okay. Voltage gain means the V naught over the input, which is Vs. So it's 5,333 around that. Okay. To the current, similar thing. 2 ohms law, right? 2 ohms law. Input current equals to input source divided by the 2 series connected resistor in the loop. Output current equals to the generated voltage divided by the 2 series connected resistor in the loop as well. Both current end up with in terms of V in, but so what? You do a division between them, the V in is canceled out. End up with 2 times 10 to the 9. This is the result. This is the result. Okay. Voltage and current gain. Okay. Voltage and current gains. A little bit algebra. What you applied is nothing more than voltage divider and Ohm's law. Okay. This is the homework. And once again, homework number 3 is the most important one. And number 2 is obviously only I think only one student probably. That 10 out of 10 guy get it. But very impressive. Good job. But if not this time, that's okay. Just get used to 1 DC, 1 AC. It's just a plus in the middle. You can't do any more than that. Okay. And you need to analyze the DC circuit, which is different from the AC circuit. Okay. 2 different circuits. You come up with 2 results and then sum them up. That's what we're gonna do in this entire course. 1 AC source, 1 DC supply. So you need to conduct 2 respectively. We still have well, it's a surprise that we have some time left. Okay. Any questions you have regarding this course, regarding homework, regarding the knowledge, and regarding what are we gonna do next? Any questions we have here? I think just a 1 exam time survey to be conducted. Okay. As Kevin's wish, thank you for attending today's lecture, and talk to you guys on Thursday then. Okay. Bye now.